Welcome back to AP Physics C, the Electricity Magnetism course, Unit 1 for Electrostatics. In this video, we're going to discuss point charges. Even though we're going to talk about point charges in this video, all the equations that you're going to see can apply to really any electric field, any electric potential energy, and any electric potential. Okay, it's just that point charges are going to be the easiest to study this around. So in order to bring two like charges near each other, so like if I want to bring a positive charge towards that positive charge in the middle there, I'm going to have to do work on the object or on the test charge, right? Or if I want to pull, basically, remember, opposite attract like repel. So I want to kind of squeeze these together, or I'm going to pull apart opposite charges, okay? So I have to do work. I have to exert a force on it, right? And so remember, the work equation is going to be Fe, right? The electrostatic force, which is what we're going against, times the distance we move those charges. But remember, the electrostatic force has a equation. I'm going to replace the R with a D. I know usually we use R, okay? And so these are going to, the distance up top is going to cancel the distance on the bottom. And so we have this equation, KQ1 Q2 over D. That is what we know as electric potential energy, okay, or a change in electric potential energy. So UE is simply K Q1 Q2 over R. So electric potential energy is what we're doing is when we move these charges apart, it's just the amount of energy needed to move that charge against an electric field. And we say against it because, remember, positive charge wants to flee a positive charge. Negative charge wants to go towards a positive charge, right? So we have to do work against that field to move those charges. Now, when you talk about work per unit charge, right, we get something called electric potential, or this is also known as voltage, okay? And so to find the amount of electric potential, we're just simply going to do what the definition is, work per unit charge. And I put a G. A very common mistake for me. I like to switch those letters around. Okay, so work per unit charge. So that also gives us, we can look at the change in electric potential. Remember, it's still work per unit charge. Okay, and you can manipulate this equation how you want. So like if we were to solve this for work, this would be work, pen back. So work equals Q delta V. Now, one thing to remember is that much like the electrostatic force, right, the further we get away from the point, the electric field is going to weaken, which means then the electric potential is going to weaken. So remember, electric field strength, KQ over R squared, right? As this gets bigger, that E is going to go down, right? So as R goes up, E will go down, okay? And this is going to hold true for electric potential energy as well. And so the change in voltage can be determined by using the equation delta V equals KQ over R. And there is a mathematical relationship between E and delta V. E is negative dV dx. Okay, or dV dr, dV dd, whatever you want, whatever symbol you're using, which means then also delta V is also equal to the negative integral of E dx. Okay, so I'm showing you that here, but this is going to be applied later in a couple of videos when we talk about like just point, when we talk about like Gauss's law and electric flux. That's going to be an important equation. But you can see how related they are, right? You got KQ over R for one, you got KQ over R squared. So as you see, as I increase this, that delta V is going to go down. Now, some things to remember, so they're not bullet points here, but some things to remember is that that charge, right up here, charge goes from high V right? High potential to low V, right? Because sometimes they may give you a question where it's like, hey, which way is this going to point? Remember, it always goes from high to low. And what you see in this diagram, these circles, right, that are kind of surrounding this charge, those are not electric field lines. Those are what we call equipotential lines. And they just show you where the voltage is the same, or that electric potential is the same. Okay, and one way to equate this is like topography maps, right? So you know how, where you're kind of like where the steepness is based on how close they are, right? Same thing with electric fields. The closer the equipotential lines are, right, the stronger the field is there, right? So when we talk about electric fields, we talk about how the electric field is, if there's more lines per area there, the electric field is stronger there. Well, it holds true, right? The same thing for equipotential lines. The more lines that you are, the closer those lines are, the stronger the field is. Okay. All right. So let's look at an example problem. So here we have a diagram showing these lines produce an unknown charge distribution. You got points A, B, C, and D. Part A, describe the direction of the electric field at point A. At point B, at which point is the electric field have the greatest magnitude? And C, how much network must be done in moving a charge, a negative 1 microcoulomb charge from rest to point C and to rest at point E. Okay, so if you look at the different points, one thing to note is that the E field lines and the equipotential lines, they're going to be perpendicular to each other. So, and remember, perpendicular pointing high to low, right? Perpendicular pointing from high V to low V, right? So that's what we're going to do for the first, for part A, is we know it's going to be perpendicular to these equipotential lines, and it's going to point from the 5-volt equipotential line to the 0-volt equipotential line, right? So it's going to go up and to the right, right? You can say perpendicular to the line, right? Again, pointing from high to low, okay? Now, at which point does electric field have the greatest magnitude? Well, that's very easy. See all these areas, or the lines around B? One of the last things I said right before we moved into this example problem was the more, the closer the lines are together, right, the stronger the field is at that point. So this is going to be at point B, okay? If you want to kind of say where is it the weakest, right, it's kind of in this C area, right? So this is where it would be the weakest because the lines are more spread out. All right, the last question here: how much network must be done by an external force to move the negative 1 microcoulomb point charge from rest to point E? Well, we're going to use work equals Q delta V. Okay, and so a couple things to remember. This needs to be put into coulombs, so that's going to micro. Remember, is 1 times 10 to the negative 6th. So all we're going to do is substitute that in. And then our delta V, so we're going to go from C to E. So we're going to start, our initial is 20 volts. Our final is 10 volts. So we're going to do negative 1.0 times 10 to the negative 6 coulombs times 20 minus 10. Okay, so that's going to be a value of 10. And so the amount of work that we have to do is 1.0 times 10 to the negative 5th joules. Okay, and so remember, work is a transfer of energy, right? So we're either increasing or decreasing the amount of energy that is possessed. So you can see here, this in moving from C to E, it's actually going to lose energy. How do we know it's going to lose energy? Because we ended up with a negative number. Okay, we could also, at this point, we can figure out, now that we know this value, we can go and figure out, what is that central charge type situation. But that's point charges. Again, we start with point charges because it's the easiest thing to look at, right? Because it's a single point producing lines. In most situations, right, even though these equipotential lines are kind of like curved and all that, that means there's multiple point charges sitting in that region. In the next video, now we're going to start talking about Gauss's law, And Gauss's laws is where we're going to start bringing in the calculus aspect of this unit.